guys, we're talking about derivatives of exponential functions with a base of e. All right, so think about what that means. E, exponential functions with a base of e. So, for example, like y equals e to the x, or y equals e to the 2x, and things like that. Exponentials has a base of e. So, we want to understand how we find its derivative, and also how we can use it. So, let's think first. What's the definition of e? Now, don't forget that e is a number. It's an irrational number. It's in the same family as pi. It's equal to, because I'm rounding, 2.72. But we want to think about where it comes from. And there's many ways that we can develop this constant. And we're going to focus on developing it through derivatives. Okay, so right here, two things that I just want to show you guys right now. We know that e is equal to the limit as h approaches infinity of 1 plus 1 over h to the h. It's okay if you didn't know that. Something that's really similar but just slightly different is that e is also equal to the limit as h approaches 0 of 1 plus h to the 1 over h. So what we're going to do right now is we're going to be taking these derivatives so that way we can figure out what is the derivative of e to some power, okay, of e to the x. Now, because this one has a limit as h approaches 0, which is similar to our limit definition, remember that was very similar, the limit as h approaches 0 of f of x plus h minus f of x all over h. We're going to really focus on this one, but I just want to make sure you guys are aware that these are really similar and they both equal e. Okay, so what is the derivative of e to the x? Now, I'm going to show you guys a nice little, I guess you could call it a proof, of how to find the derivative of e to the x. You won't be asked to derive this on your own. Like, I'll never ask you to do that, but it's pretty cool. It's something that I want to show you guys, and because I'm not ever going to ask you to do it on your own, you don't have to write it necessarily, but if you want to, go ahead. So, let's let f of x equal e to the x. Therefore, we're trying to find its derivative. Woo. So, we're going to use our limit definition. Limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. Well, let's substitute in our function. So now I have e to the x plus h minus e to the x all over h. Again, the purpose of this is to find out what the derivative of e to the x is. Now, using my rules of exponents, I can rewrite this as e to the x times e to the h. Right, that's one of our rules that we've known. And now I could take out a GCF of e to the x in my numerator, and remaining I would have e to the h minus 1 all over h. Okay? Let's show some side work here. Now, here I have this e to the h, which we're not sure at this point yet what that represents. But remember just before, on my previous page, we said that e is equal to the limit as h approaches 0 of 1 plus h all to the 1h power. Okay, well, if I put both sides to the h power, well, now, again, think this is when h is really small. Or in other words, you know, the limit as h approaches 0, h is really small. There's a really small difference here. So if I put both sides to the h power, well, then we see that e to the h is about equal to 1 plus h when h gets infinitely small. So now I can use that information here to replace e to the h with 1 plus h. Notice that my 1's are going to cancel now. And we're almost there. Now I have e to the x times h all over h, but those guys cancel. And using direct substitution, we see that the limit as h approaches 0 of e to the x is e to the x. All that work just to find out that the derivative of e to the x is itself. Pretty cool. Now, like I said, I'm not ever going to ask you guys to reproduce this, but it's just something that I wanted to show you to help us understand what the derivative of an exponential is. So, now, one thing that I want to let you guys know is that this exponential with a base of e is the only function that has this property, okay, that its derivative is itself. Unless you're talking about like the derivative of y equals 0. Obviously, its derivative is 0. So, the rate of change, derivative, of e to the x is the height of e to the x, is its y value. One thing that I want to keep in mind, because it won't always be just e to the x, it might be e to the 2x. And if we do have exponents, geez Louise, if we do have exponents that are more complex, where it's not just x and it's, you know, multiple operations happening, we do need to use our chain rule. So for example, if I had e to the 2x, its derivative would be itself times the derivative of its exponent, which is 2. I suppose you could multiply by the derivative of x, but that's just 1. Okay, so here's our first example. Find the derivative of f of x. Go ahead, put me on pause. So this derivative of this exponential is itself e to the 3x squared minus 2x times the derivative of its exponent, which is 6x minus 2. Go ahead and try this next one. Awesome. So its derivative is itself e to the negative 3 over x times the derivative of its exponent, which is 3x to the negative second. Here could be a nicer version of it just so we don't have negative exponents. All right. Next example, we want to find relative extrema. Don't forget that we could use our first derivative test to do so. So therefore we have to find its first derivative. Don't forget to use derivative speak. So go ahead and put me on pause. Time to check our work. So if you didn't identify that you needed to use your product rule here, you might not have gotten this right. So since we have a product, we use our product rule. I factored out a GCF, and then I set each of those factors equal to 0. Now notice that when I set e to the x equal to 0, well, think about the graph of e to the x. Okay, well, there's a horizontal asymptote at 0. Okay, so that can't be a critical number, but I do get negative 1. I plotted my increasing, decreasing chart using my first derivative test and my derivative speak. I said since f prime of x is less than 0, on negative infinity to negative 1, and f prime of x is greater than 0 on negative 1 to infinity, we know that at the point negative 1 over e is a relative min. All right, let's have you guys try this one. So this time we're looking for inflection points. So now you know that we need a second derivative. Notice that it doesn't ask anything about extrema or increasing, decreasing, so you don't even need to make an increasing, decreasing chart. So go ahead, put me on pause, and then we'll check our answers. Alrighty, so let's see if I can get rid of this. No product rule needed here. I did have to use my chain rule, so my first derivative, it's the exponential times the derivative of its exponent, which is negative x. Find the second derivative, now I have to use my product rule. So if the first times with the second, plus the second times with the first. I simplified that a little bit here in terms of signs, condensing, and then I factored out GCF of negative e to the negative x squared minus over 2, all over 1 minus x squared. When I set each of these factors equal to 0, once again, notice that this exponential, when I set it equal to 0, well, there's a horizontal asymptote at 0. So that's not a possible point of inflection. But we have positive and negative 1. I put that on my concavity chart. So don't forget to find possible points of inflection, not possible points of inflection. We have to see if concavity changes signs, and in fact it does. So in my derivative speak, I wrote, since f double prime of x is greater than 0 on negative infinity to negative 1, and f double prime of x is less than 0 on negative 1 to 1, at the point negative 1 e to the negative 1/2 is a point of inflection. Likewise, since f double prime of x is less than 0 on negative 1 to 1, and f double prime of x is greater than 0 on 1 to infinity, at the point 1 e to the negative 1/2 is also a point of inflection. Great. All right, so let's find the equation of the tangent line to the curve at 0, 1. Now, as we know, we've done tons of these problems before. To find the equation of the tangent line, we're going to need a slope, and we're going to need a point. But we're already given the point, so all we need is the slope. Go ahead, put me on pause. So, finding the derivative, I do need to use the quotient rule. So I did that. Low d high minus high d low, all over low squared. Now, you might be tempted at first to simplify this numerator, but it's unnecessary. We made this so easy on you. We made the x value 0, so all you have to do is plug in 0 anywhere you see x. And don't forget that anything to the 0 power is just 1, so this ends up being 1 minus 2 over 1, which is negative 1. Now, don't forget that this negative 1 represents the slope when x is 0. So I plug that into my point slope form, and I get y equals negative x plus 1. All right, so just in conclusion, don't forget that the derivative of e to the x is e to the x. So cool. Also, if we have something else in our exponent besides just x, then we'd have to use our chain rule. And then just something to think about. Of course, we'll answer this someday. What if the base is not e? What if it's 3 to the x? What if it's 1,000 to the x? What if it's 1/2 to the x? What would happen? That's my cliffhanger for you. Good job.